In January 2026, researchers ran the same Claude language model through a scientific reproducibility benchmark twice. In the first test, it scored 42%. In the second, it scored 78%. This 36-point gap occurred without a secret prompt engineering trick or a tweaked temperature setting. The weights were identical. The training was identical. The only variable was the environment the model was placed inside. Evaluating AI by looking only at the model treats the system like a disembodied brain in a jar. This assumes raw intelligence determines whether an autonomous agent succeeds or fails. An AI model cannot execute code, search a file system, or remember a conversation. It requires a surrounding architecture called a harness to provide memory, tool execution, and state management. Model leaderboards only measure how well a system predicts the next token. In a production environment, engineering velocity depends on the architecture of the harness. Two dominant paradigms are currently shaping how enterprise software gets written. Anthropic built Claude Code, and OpenAI built Codex. Anthropic designed Claude Code around collaborative incrementalism. It is an agent built to sit alongside an engineer, executing commands directly in their local terminal environment. OpenAI designed Codex around isolated mechanical enforcement. It operates like an independent contractor, sealed in a cloud-based cleanroom where it works on a cloned copy of your codebase. Claude Code and Codex represent mutually exclusive computer science philosophies regarding how humans and AI share control. Selecting one of these agents forces an engineering organization to wire its standard operating procedures, security policies, and daily habits to fit the constraints of that specific harness. Autoregressive models, systems that generate outputs one word at a time, suffer from the blank slate problem. Every new session, the AI has zero memory of the work it completed in the previous shift. Claude Code's harness solves this by generating structured artifacts, like persistent markdown files, and reading Git history to construct a compounding memory. This forces an iterative loop, advancing safely by constantly referring back to that local text file to maintain the broader project context. The Codex harness takes the opposite approach. It relies on the repository itself as the exclusive system of record. Instead of internal memory, Codex navigates structured documentation. To prevent drift, automated linters analyze the source code, flagging errors and systematically cleaning up fragmented code. Anthropic's harness forces the agent to remember the project through local files. OpenAI's harness forces the codebase to remember the project through strictly enforced mechanical rules. Memory is only half the equation. These harnesses also dictate how agents physically execute code and interact with their host environments. Claude Code relies on a philosophy engineers call bash is all you need, granting the agent access to composable Unix primitives like grep or npm that can be chained together. By chaining these simple commands directly in the user's actual terminal, the agent operates with high flexibility and consumes very few context tokens. This requires extending your absolute trust boundary to encompass the engineer's entire local workstation. The agent has the exact same access privileges as the human. Codex executes code by cloning the repository into an isolated cloud container with its internet access disabled by default. It interacts with its environment through strict, bidirectional JSON RPC endpoints that map to the Model Context Protocol. The Model Context Protocol is an open standard that connects AI systems securely to external data sources. Your choice of execution harness directly dictates your security posture. Organizations must choose between local flexibility or strict zero-trust cloud isolation. All of these agents eventually hit a physical limit known as context bloat. As the agent works, the computational cost to process its growing history increases quadratically. Basic agents operate in an append-only mode. They permanently retain verbose trial and error logs and failed tests, which poisons the context window and degrades the model's ability to reason. To survive long horizon tasks, the harness requires a mechanism called active context compression. This chart shows context growth. The red line represents a standard agent growing monotonically, eventually hitting the limit and failing. The blue line displays a sawtooth pattern, where the focus agent autonomously compresses context, achieving 22.7% token reduction, self-regulating memory without external timers. Without a harness capable of active context compression, deploying autonomous software engineering agents for long horizon tasks is financially and computationally impossible. At the enterprise level, organizations are currently panicking over AI vendor lock-in. Being tied to a specific intelligence provider, like OpenAI or Anthropic, is already a structurally solved problem. Open standards like ONIX act as universal translators. They represent machine learning models, so they transfer easily between frameworks. This API abstraction layer lets you swap models immediately, routing requests dynamically to whichever model offers the lowest latency, cost, or best capabilities that day. Harness lock-in is the actual structural risk facing engineering leaders today. While the intelligence models are easily swappable at the API layer, a team's verification protocols, testing environments, and automation scripts become permanently entangled with the architecture of the harness sitting directly below it. Replacing a model requires a configuration change. Replacing a harness requires destroying and rebuilding an entire institutional process. Imagine an engineering team that builds a suite of custom workflows reliant on Claude Code's local bash execution and its persistent local markdown artifacts. If that team attempts to migrate to a sandboxed, repository-centric harness like Codex, the cost is catastrophic. Switching between these architectures requires a total reset of how the organization manages system state, security boundaries, and automated tasks. This architectural lock-in accumulates silently over time. Every custom connector and tailored shell script an engineer writes cements their dependence on that specific harness environment. Engineering leaders should evaluate AI coding tools as more than just simple software-as-a-service subscriptions or swappable APIs. Choosing an AI harness is a foundational architectural commitment. That decision will dictate your company's technical velocity, security posture, and workflow constraints for the next decade.